Here we are on a Monday afternoon looking at inverse functions. So let's think about this. Here I have a picture of a function machine. One comes out, one goes into the other. Now let's say that we have the number 5 goes in here. We put the 5 into the first one. X is the input. Comes out, or 2 times 5 is 10 plus 1. It comes out is 11. All right, so here we have. Now let's say we take this 11 and we put it in here. And see what comes out in the next one. Well, here we're going to have 11 minus 1 over 2, which is equal to 5. So out comes 5. Now you should notice that we started with 5, we did something to it, have an output in between, then we put that back in, and then we get 5 again. This is what we call a reciprocal function, where essentially if two functions are reciprocals of each other, they undo what the function did in the first place. So the output of the first, if you make the input of the second, you get back to the original input. All right, so in a sense, inverse functions undo the input and output. If you want to think of that, it's a crude way of thinking about it, an unofficial way. But the point being, you get back to where you want. Now, not all functions have inverses. Many do. Sometimes you have to adjust the domain. Sometimes they don't. Sometimes we have things called self-inverse functions. But let's have a look. Now, a helpful little summary from the book. We have this symbol here, f to the power of minus 1. Now, for some of you, you might remember with negative powers that if you have, say, x to the negative 1, it means 1 over x. X to the negative 1 is equal to 1 on x. That's not what this means. That's reciprocal. We're not talking about that. This is a different context. It's called the inverse, right? F to the power of negative 1x. So you also have to remember that if you have an inverse function, the actual inverse has to be a function as well. So there's an example where you could have a parabola and you find its inverse, but actually it's not a function because the inverse doesn't satisfy the vertical line test. So we need to make sure that that's true. This is an important one. It's a reflection of y equals f of x in the line y equals x, and we'll look at that. And it satisfies these two things. When you have a composite, no matter what the order, when you put the input in and you do this and you go through the two machines, you always get back to x. Whether you put the first one in, whichever order you put it in, whether you put it in f first and then f inverse, or f inverse and then f, you should always end up with what you originally started with. If that doesn't happen, then they're not proper inverse functions. And just as the final definition, y equals x is called the identity function, because you can see that if x equals 2, y equals 2. Oh, you put that in again, 2. So it's always the same output as it is for the input. So it's a unique case. It's also self-reciprocal, if you can put it that, self-inverse, sorry. It's a self-inverse function, and we call it the identity function. All right. Now, how do we find a reciprocal? Well, it's actually very straightforward algebraically. To find f inverse x, we swap the x and y and then make y the subject. That's what we're used to seeing. So we see here, if f of x is equal to 3x minus 4, so we can say y equals 3x minus 4, this step here, I've just swapped the x and the y. Just swap them over. So x equals 3y minus 4. Add the 4 to both sides. You get x plus 4 equals 3y. I've just switched this order around and divided by 3. So y is equal to x plus 4 on 3. Now this means that y equals 3x minus 4 and y equals x plus 4 over 3 are inverse. Now let me just go over here and illustrate this point of the composite function. So I've got f of x is equal to 3x minus 4. F inverse x is equal to x plus 4 over 3. Now, the composite function, f composite f inverse of x, we take the f inverse, this guy here, and we pop it in for x and see what we get out. Equals 3 outside of x plus 4 on 3 minus 4 equals. The 3 outside of 3, well, the denominator and the numerator, the factor of 3, they're going to, if you like, divide out. So I'm just going to be left with x plus 4 minus 4, and that surprisingly is equal to x. So that's the first part satisfied. What about the other one? Let's find f inverse composite f of x equals. Well, so basically this works the other way. We take this and we pop it in to here, where x is. All right, let's have a look. So we're going to take x, 3x minus 4, so we're going to get 3x minus 4 plus 4 over 3, which is equal to, well, it's 3x over 3, which is also equal to x. So you notice that both composites, the orders, are both equal to x. Therefore, we've double-checked that they are inverse of each other. That's good. Now, when we graph inverse functions, the curves are reflected in the line y equals x, right? So that's helpful. Now, if we just flick over to my favorite little Desmos app, do you see here the orange line? The orange line is y is equal to 3x minus 4. All right, so that's helpful. Then I've got a purple line, which is the one that we found is a reciprocal. Now, what's the relationship? Well, if I put in my dotted line of y is equal to x, do you see? You can see quite clearly, actually, that they are reflections of each other. So if you put a mirror up along the dotted line, you would see that that's, in fact, exactly the reflection. The purple and the yellow reflect each other. So again, we could either have done that by observation and tried to sort of do that. It's a bit difficult to do. Or we can just kind of illustrate the point that, yes, that's another way we can check that two things are inverse functions of each other. Now I'll put that into the notebook in a sec, so you'll see that as well. Now, another thing that we can do is, well, we can check if the inverse functions by using the input and output. So f of 5 is equal to, well, 3 times 5 minus 4, which is equal to 11. Now, f inverse of 11 is equal to, what was it? It was x plus 4 over 3. Not x, sorry. It was 11. 11 plus 4 over 3, which is 15 over 3, which is equal to 5. So here we have it. We've gone from 5, we got 11, put 11 in, we get back to 5. So give ourselves a tick, because we're saying that, yes, it is in fact that they are reciprocals of each other. Not reciprocals, they're inverse of each other. Don't say the word reciprocal. They're inverse functions. That's me not thinking straight. Now, this, I'm going to put a red box around this because this is an important point for you to take note of. When a function f of x has an inverse, the domain of f of x becomes the range of f inverse x, and the range of f of x becomes the domain of f inverse x. So do you see that the range and domain swap? Just like we swapped the x and y coordinates, it means that the range and domain switch based on whether something's an inverse. Now, if I jump back to my Desmos thing, I'm going to illustrate this point. Here we have a point up here. Let's choose this one. I'm going to just go up here, and hopefully this will show. Now, do you see that this point, 820 sits on the line, on the yellow line? Now, if I have 8.820, there's an interesting thing that I can say with absolute confidence that 28 sits on the purple line. I'll find out. Here we have, we're going to come across here. Where is it? 28 sits on that. So if I want to find coordinates on an inverse function, I simply reverse the x and the y. So another way to think about this is all coordinates of an inverse function are the reverse of coordinates of the function. So what I mean is, i.e., if 28 sits on f of x, 820 will sit on f inverse x. And that's always going to be true. So we can use that information to be able to then manipulate and find information about the inverse that we want to find. Now, there are a few questions that we're going to have a go at in the exercise, which in the standard level book is 2G. Exercise 2G. There's a few questions which might seem a bit left field. Things like using coordinate geometry and the gradient of y equals f inverse x. Just have to remember that. See if you can find something about the gradient. But if I just pop back over to here, do you notice that the gradients of this, the gradient of the yellow line is 3. The gradient of the purple line is 1/3. When you multiply the two, they multiply to 1. Now, I want you to think about that. See if that's always the case and why that might be the case. But there is an interesting thing, so try out a few. So we can, in fact, use the gradient to help us graph the curves and see what else is happening. So that's basically kind of to have a quick look at inverse functions. You can do it graphically if you're careful. We can do it algebraically by switching the x and y coordinates. We can test the composite to make sure that the input and output match up when you do it into the function itself and then into the inverse. And we'll also be having a look at what's called a self-inverse function, which essentially graphically means it's reflected along the line y equals x. But I'll let you have a look at that. So again, if you have any questions, let's send me an email, ask me in class, but happy inverse functioning. All right.